Hello everyone, and welcome back to another AI article. I saw we picked up 2 subscribers, and if you're coming back for this content, welcome back. If you're here just for more cat videos, don't worry, those will be up as well, although admittedly they're mostly shorts. Anyway, it's the end of my day, and I looked outside and saw all the snow's coming, but I can't complain because it's nothing compared to what the rest of the country's going through. But it's time for professional development hour because my brain is toasted from, mostly doing setups. Setups and deadups and setups forever, and interface changes. Anyway, without much further ado, we have the automated design of agentic systems. And as we talked a little bit in the last paper we looked at, agents are the hot new thing. We no longer have large language models. We have large language models, plus tools and an orchestrator to conduct the thing. I don't know why they wouldn't have called it a conductor, but that probably, screw people up. Anyway, Lu and Clune from University of BC. Researchers are investing substantial effort in developing powerful general-purpose agents wherein foundation models are used as modules within agentic systems. However, the history of machine learning teaches us that hand-designed solutions are eventually replaced by learned solutions. We formulate a new research era, Automated Design of Agenic Systems, ADAS, which aims to automatically create powerful agentic system designs, including inventing novel building blocks and/or combining them in new ways. We further demonstrate that there is an unexplored yet promising approach within ADAS where agents can be defined in code and new agents can be automatically discovered by a meta-agent, programming even better ones in code. Given that programming languages are Turing complete, this approach theoretically enables the learning of any possible agentic system, including novel prompts, tool use, control flows, and combinations thereof. We present a simple yet effective algorithm named meta-agent search to demonstrate this idea, where a meta-agent iteratively programs interesting new agents based on an ever-growing archive of previous discoveries. Through extensive experiments across multiple domains, including coding, science, and math, we show that our algorithm can progressively invent agents with novel designs that greatly outperform state-of-the-art hand-designed agents. Importantly, we consistently observe the surprising result that agents invented by meta-agent search maintain superior performance, even when transferred across domains and modules, demonstrating their robustness and generality. Provided we develop it safely, our work illustrates the potential of an exciting new research direction toward automatically designing ever more powerful agentic systems to benefit humanity. Assuming you haven't read sci-fi, and then they go rogue, and everything's crazy. This does look like a long article, but a lot of it is appendices, so I know it's going to be a lot of tight reading in terms of the single spacing, but don't worry about it being super long. Hopefully this won't be more than 45 minutes. Foundation models such as GPT and Claude are quickly being adopted as powerful general-purpose agents for agentic tasks and need flexible reasoning and planning. Despite recent advancements in functional foundation models, solving problems reliably often requires an agent to be a compound agentic system with multiple components instead of a monolithic model query. Additionally, to enable agents to solve complex real-world tasks, they often need access to external tools such as search engines, code execution, and database queries. As a result, many effective building blocks of agentic systems have been proposed, such as chain of thought planning and reasoning, memory structures, tool use, and self-reflection. Although these agents have already seen significant success across various applications, developing these building blocks and combining them into complex agentic systems often requires domain-specific manual tuning and substantial effort from both researchers and engineers. However, the history of machine learning reveals a recurring theme. Manually created artifacts become replaced by learned, more efficient solutions over time as we get more compute and data. An early example is computer vision, where hand-designed features like HOG were eventually replaced by learned features from convolutional neural networks. More recently, AutoML models, AI-generating algorithms, have also demonstrated the superiority of learned AI systems compared to hand-designed AI systems. For example, the current best-performing models come from neural architectural search instead of manual design. In LLM alignment, learned loss functions outperform most hand-designed ones, such as DPO. The AI scientist demonstrates an automated research pipeline, including the development of novel machine learning algorithms, and an endless number of robotics learning environments can be automatically generated in works like OmniEpic, which demonstrates surprising creativity in generated environments and allow more efficient experiment creation than the manual approach. More examples in section 5. Therefore, in this paper, we propose a new research question. Can we automate the design of agentic systems rather than relying on manual efforts? So here's an overview of the proposed algorithm meta-agent search and examples of discovered agents. So in our algorithm, we instruct the meta-agent To iteratively program new agents, test their performance on tasks, and add them to an archive of discovered agents, and then use this archive to inform the meta agent on subsequent iterations. We show 3 example agents across our runs with all names generated by the meta agent, and detailed code of examples is in Appendix F. So let's just look at this. So the agent archive can have this divide and conquer agent where the task is to divide the problem and then send all the subparts out to experts for answers and then ensemble it and produce a final answer. We have what's called a verified multimodal agent. So the task is given to the visual analyzer, which creates a visual paradigm, which goes to a verifier, which goes to a verified paradigm, and then goes to COT. Not quite sure what that's an abbreviation for before it returns an answer. And then there's multi-step peer review agent, where there's tasks which get sent to experts. They all generate an answer. The answer goes to a bunch of reviewers, and then this iterates over and over again until we have a good answer, presumably. All right. So to explore the above research question, we formulate a new research area we call Automated Design of Agenic Systems, ADAS, or ADAS, which aims to automatically invent novel building blocks and design powerful agentic systems. We argue that ADAs may prove to be the fastest path to developing powerful agents and show initial evidence that learned agents can greatly outperform hand-designed agents. Considering the tremendous number of building blocks yet to be discovered in agentic systems, it would take a long time for our research community to discover them all. Even if we successfully discover most of the useful building blocks, combining them into effective agentic systems for massive real-world applications would still be challenging and time-consuming, given the many different ways the building blocks can combine and interact with each other. In contrast with ADAS, the building blocks and agents can be learned in automated fashion. ADAS may not only potentially save human effort in developing powerful agents, but could also be a faster path to more effective solutions than manual design. Although a few existing works can be considered as ADAS methods, most of them focus only on designing prompts, greatly limiting their ability to invent flexible design patterns in agents. In this paper, we show that there is an unexplored yet promising approach to ADAS where we can define the entire agentic system in code, and new agents can be automatically discovered by a meta agent, programming even better ones in code. Given that most programming languages, such as Python, which we use in this paper, are Turing complete, searching within a code space theoretically enables an ADAS algorithm to discover any possible agentic systems, including all components such as prompts, tool use, control flows, and more. Furthermore, with recent foundational models being increasingly proficient in coding, we can use foundational models as a meta agent to create new agents in code for ADAS, enabling novel agents to be programmed in an automated manner. Following the aforementioned ideas, we present meta-agent search in this paper as one of the first algorithms in ADAS that enables complete design in code space. The core concept of meta-agent search is to instruct a meta-agent to iteratively create interestingly new agents, evaluate them, and add them to an archive that stores discovered agents, and use this archive to help the meta-agent in subsequent iterations create yet more interestingly new agents. Similar to existing open-endedness algorithms that leverage human notions of interestingness, we encourage the meta-agent to explore interesting, i.e. novel or worthwhile agents. To validate the proposed approach, we evaluate the proposed meta-agent search on the challenging ARC logic puzzle task that aims to test general intelligence of an AI system, 4 popular benchmarks on reading comprehension, math science questions, and multitask problem solving, and the transferability of discovered agents to held-out domains and models. Our experiments show that the discovered agents substantially outperform state-of-the-art hand-designed baselines. For instance, our agents improve F1 scores on reading comprehension tasks in DROP by 13.6 and accuracy rates on math tests and MGSM by 14.4%. Additionally, they improve accuracy over baselines by almost 26% and 13% on GSM-AK and GSM hard math tests, respectively, after transferring across domains. The promising performance of our algorithm over hand-designed solutions illustrates the potential of ADAS in automating the design of agentic systems. Furthermore, the experiments demonstrate that the discovered agents not only perform well when transferring across similar domains, but also exhibit strong performance in transferring across dissimilar domains, such as from mathematics to reading comprehension. This highlights the robustness and transferability of the agentic systems discovered by meta-agent search. In conclusion, our work opens up many exciting research directions and encourages further study. So the automated design of agenic systems. And yes, I'm going back and forth between saying ADAS and ADAS. Kind of want to say ADAS, but it doesn't always sound right to me. Anyway, at the time of writing, the community had not reached a consensus on the definitions or terminologies of agents. Here by agents, we refer to agenic systems that involve foundation models as modules in the control flow to solve tasks by planning, using tools, and carrying out multiple iterative steps of processing. In this paper, we propose a new research area, Automated Design of Agenic Systems, ADAS, similar to research areas in AIGAs and AutoML, and such as neural architecture search. We formulate ADAS as an optimization process and identify 3 key components of ADAS algorithms. So, figure 2, the 3 key components. Search space was determined which agenic systems can be represented at ADAS. The search algorithm specifies how the ADAS method explores the search space. The evaluation function defines how to evaluate a candidate target on target objectives such as performance. So we have like agents defined by code, and then it uses the code and it samples it, it does a little accuracy on the task, and then it evaluates, how that's relative to the objectives. So, automated design of agenic systems involves using a search algorithm to discover agenic systems across a search space that optimize an evaluation function. So, if you were like, what did that just say? Search space. The search space defines which agenic systems can be represented and thus discovered in ADAS. For example, works like Prompt Breeder mutate only the text prompts of an agent, but their other components, such as control flow, remain the same. Thus, in these search spaces, agents that have different control flow than the predefined one cannot be represented. Existing works also explore search spaces, such as graph structures and feed-forward networks. So there's different kinds of search spaces. Yeah, okay. This is a little over my head. I won't lie. If you understand this better than I do, feel free to leave comments. I am totally open to being schooled. So yeah, different control flow. Okay. Search algorithm. Search algorithm defines how ADAS algorithms explore the search space. Since the search space is often very large or even unbounded, the exploration trade-off should be considered. Ideally, the algorithm can both quickly discover high-performance agenic systems and avoid remaining stuck in a local optimum. Oh, that's just my life, stuck in a local optimum. Existing approaches include using reinforcement learning or foundation models, iteratively generating new solutions as search algorithms. The evaluation function. Depending on the application of the ADAS algorithm, we may consider different objectives to optimize, such as performance, cost, latency, or safety of agents. An evaluation function defines how to evaluate a candidate agent on those objectives. For example, to assess the agent's performance on unseen future data, a simple method is to calculate the accuracy rate on the validation data for a task, which is commonly adopted in the existing works. Although many search space designs are possible and some have already been explored, there is an unexplored yet promising approach where we can define the entire agenic system in code, and new agents can be automatically discovered by a meta agent programming even better ones in code. Searching within a code space theoretically enables the ADAS algorithm to discover any possible building blocks in agenic systems that combine any of these building blocks in any way. This approach also offers better interpretability for agent design patterns, since the program code is often readable, making debugging easier and enhancing AI safety. Oh, that would be nice. Natural language processing sometimes is my friend. Anyway, additionally, compared to search spaces using networks or graphs, searching in a code space allows us to more easily build on existing human efforts. For example, it's possible to search within open source agent frameworks like LangChain and build upon all existing building blocks. Finally, since foundation models are proficient in coding, utilizing a code search space allows us to leverage existing expertise from foundation models during the search process. In contrast, search algorithms and custom search spaces, such as graphs, may be less efficient due to the absence of these priors. Therefore, we argue that the approach of using programming languages as the search space should be studied more in ADS. So, meta-agent search. In this section, we present meta-agent search, a simple yet effective algorithm to demonstrate the approach of defining and searching for agents in code. The core idea of meta-agent search is to adopt foundational models as meta-agents to iteratively program interestingly new agents based on an ever-growing archive of previous discoveries. Although any possible building blocks in agenic systems can theoretically be programmed by the meta-agent from scratch, it is inefficient in practice to avoid providing the meta-agent any basic functions such as foundational model queries or APIs or existing tools. Sorry, I'm not the greatest with abbreviations. I try. Therefore, in this paper, we define a simple framework within 100 lines of code for the meta agent, providing it with a basic set of essential functions like querying foundation models or formatting prompts. As a result, the meta agent only needs to program a forward function to define a new agenic system similar to the practice in FunSearch. This function takes in the information of the task and outputs the agent's response to the task. Details of framework codes and examples can all be found in Appendix B. As shown in Figure 1, the core idea of meta-agent search is to have a meta-agent iteratively program new agents in code. We show the main prompt for the meta agent to program new agents below, where variables in the prompts are highlighted. Similar to existing open-endedness algorithms that leverage human notions of interestingness, we encourage the meta agent to explore interestingly new, novel, worthwhile agents based on ever-growing archive of previous discoveries. We also adopt self-reflection iterations in our meta agent, where it performs 2 iterations of refinement on the novelty and correctness of the proposal, and performs up to 3 refinements when errors occur while running the code. Full details in Appendix A. After a new agent is generated, we evaluate it using the validation data from the target domain. Here we calculate the performance, success rate or F1 score, and 95% bootstrap confidence interval as metrics for the meta agent to maximize. The generated agent is then added to the archive with the evaluation metrics, and the iteration continues with the updated archive until the maximum number of iterations is reached. So here's the prompt. You are an expert machine learning researcher testing different agenic systems. Give them the domain, give them the code, give them output instructions examples, discover the agent archive, initially with baselines, updated every iteration, and your task. You are deeply familiar with prompting techniques and the agent works from the literature. Your goal is to maximize performance by proposing interestingly new agents. Use the knowledge from the archive and inspiration from academic literature to propose the next interesting agentic system design. So here are the experiments. So we conduct extensive experiments on the challenging ARC logic puzzle task, 4 popular benchmarks assessing the agent's abilities on reading comprehension, math, science questions, and multitask problem solving, the transferability of the discovered agents on ARC to 3 held-out models, and the transferability of discovered agents on math to 4 held-out math tasks and 3 tasks that are beyond math. Across all the experiments, we found the discovered agents substantially outperform baseline state-of-the-art hand-designed agents. Notably, our discovered agents improve over baselines on reading comprehension tasks and drop, and on math tasks and MGSM. Additionally, our discovered agents improve over the baseline ARC test by 14% after transferring from 3.5 to GPT-4, and by 26% and 13% after transferring from MGSM math tests to held-out math texts in GSM 8K and GSM hard, respectively. All code prompts are variable at exciting diagrams. So, meta agent search on the ARC, LMM debate, and then we go up to this chain of thought. We have self-refining, we have quality diversity. So initially tested generating high-level strategies before implementing low-level details at about here. And then important strategy emerged about here, using multiple COTs to generate possible answers and then refining them and ensembling the best answers. We introduced dynamic memory for doing more refinements, scaled it up. Best agent, introduced multiple critiques for enhanced refinement. And then we have the best discovered agent on ARC. So the tasks was sent out to 5 COTs, got 5 different answers, do a human-like critic, give it some feedback, do the refinement loop like 3 times. But these answers also send out to efficiency, readability, simplicity, and that gives back feedback, and then finally spits out all answers, evaluates, throws out the top 3, ensembles it, and gives you a final answer. That's the one thing I don't really like about AI is this concept of final answers. Anyway. Certainty. Certainty. It's all about the certainty. Alright, so meta agent search progressively discovers high-performance agents based on ever-growing archive previous discoveries. We report the median accuracy of the 95% bootstrap confidence interval in a held-out test set by evaluating agents 5 times. The visualization of the best agent discovered by meta agent search on the ARC challenge details in Appendix C. So, we first demonstrate how meta agent search discovers novel agenic systems and outperforms existing state-of-the-art hand-designed agents in the abstraction and reasoning corpus challenge. This challenge aims to evaluate the general intelligence of AI systems and their ability to efficiently acquire new skills. Questions in the ARC include showing multiple examples of visual input-output grid patterns, the AI system learning the transformation rule of grid patterns from examples, predicting the grid output grid pattern given a test input grid pattern, since each question in the abstraction reasoning corpus has a unique transformation rule, it requires the AI system to learn efficiently, with few-shot examples leveraging capabilities in number counting, geometry, and topology. Following common practice, we require the agent to write code for the transformation rule instead of answering directly. We provide tool functions in the framework. They evaluate the generated transformation code. Given the significant challenge the ARC poses to current AI systems, we sample our data from questions with grid dimensions in the public training set EASY. We sample a validation set and a test set with 20 and 60 questions respectively for searching and testing. We calculate the validation test accuracy of an agent by assessing it over the validation test sets 5 times to reduce the variance from the stochastic sampling of foundational models. We evaluate all discovered agents on the held-out test set and report the accuracy in Figure 3. Meta-agent search runs for over 25 iterations, and the meta-agent uses GPT-4. Well-discovered agents and baselines are evaluated using GPT 3.5 to reduce computation costs. More details can be found in Appendix C. The baselines. We compared against 5 state-of-the-art hand-designed agents, chain of thought. Okay, so that's COTIC. Never remember, which instructs the agent to output the reasoning before answering to improve complex problem solving through intermediate steps. Self-consistency with chain of thought, which enables multiple parallel answers and chain of thought to produce a more accurate answer. Self-refine, which allows iterative self-reflection to correct mistakes made in previous attempts. Large language model debate, which enables different large language models to debate each other, leveraging diverse perspectives to find better answers. Quality diversity, a simplified version of intelligent Go Explore, which produces and ensembles diverse answers to better explore potential solutions. We also use all baselines as initial seed in the archive for meta-agent search. More details can be found in Appendix E. So, as shown in Figure 3A, meta-agent search effectively and progressively discovers agents that perform better than state-of-the-art hand-designed baselines. Important breakthroughs are highlighted in the text boxes. As is critical in prior works on open-endedness and AIGAs, and meta-agent search innovates based on a growing archive of previous stepping stones. For example, an important design pattern emerged in Iteration 3, where it uses multiple chain of thoughts to generate possible answers, refines them, and finally ensembles the best answers. This became a crucial stepping stone that subsequent designs tended to utilize. Additionally, the best discovered agent is shown in Figure 3B, where a complex feedback mechanism is adopted to refine the answers more effectively. Careful observation of the search progress reveals that this sophisticated feedback mechanism did not appear suddenly. Instead, the ideas of incorporating diverse feedback, evaluating for various specific traits, such as efficiency and simplicity, and simulating human-like feedback, emerged in iterations 5, 11, and 12, respectively. The final mechanism is an innovation based on these stepping stones. This illustrates that even though these stepping stones did not achieve high performance immediately upon emergence, later discoveries benefited from these innovations by combining different stepping stones, resembling crossover in evolution via large language models. Overall, the results showcase the potential of ADAS and the effectiveness of meta-agent search to potentially progressively discover agents that outperform state-of-the-art hand-designed baselines and invent novel design patterns through the innovation and combination of various stepping stones. So kind of like winning everything, you may end up with some dead ends, but it may end up getting recombined later, so good stuff. Alright, so reasoning and problem solving. Next, we investigate the potential of our algorithm to improve the capabilities of agents across math, reading, and reasoning domains. We test meta-agent search on 4 popular benchmarks: DROP for evaluating reading comprehension, MGSM for evaluating math capability under a multilingual setting, MMLU for evaluating multitask problem solving, and GPQA for evaluating the capability of solving hard graduate level questions in science. The search is conducted independently within each domain. Meta-agent search runs for 30 iterations. The meta-agent uses GPT-4, while the discovered agents and baselines are evaluated using GPT 3.5. More details about datasets and experiment settings can be found in Appendix D. And I'm just going to go back up here and look at this table real quick. I don't know if it's going to help me much or not. So performance comparison, meta-agent search discovers superior agents compared to baselines in every domain. And it was all conducted independently, so accuracy, so points, plus or minus, within percentages. Okay. Okay. It definitely beat all that if we're going by these numbers. Not quite sure what those numbers mean, but that's okay. We adopt all baselines introduced in Section 4.1. Additionally, since the above domains require strong reasoning skills, we include 2 additional baselines that specifically focus on enhancing reasoning capabilities of agents for a more thorough comparison. Step back abstraction, which instructs agents to first consider the principles involved in solving the task for better reasoning. And role assignment, which assigns different roles to foundational models similar to Zhu et al. To obtain better answers. More details about the baselines can be found in Appendix E. Results and analysis. The results across multiple domains demonstrate that meta-agent search can discover agents that outperform state-of-the-art hand-designed agents. We want to highlight the substantial gap between learned agents and hand-designed agents in the reading comprehension and math domains, with improvements in F1 scores by 13.6 and accuracy rates by 14.5%, respectively. While meta-agent search also outperforms baselines in the multitask and science domains, the gap is smaller. We hypothesize that for challenging questions in the science and multitask domains, the knowledge in foundational models is not sufficient to solve the questions, limiting improvement through optimizing agenic systems, which is a problem that will diminish as foundational models improve. In contrast, the reading comprehension and math domains, foundational models possess adequate knowledge to solve the questions, and errors can mainly be hallucinations or calculation mistakes, which can be mitigated through well-designed agenic systems like the ones discovered by meta-agent search. Overall, the results across various domains showcase the effectiveness of meta-agent search in searching for agents tailored to specific domains. This could be increasingly useful for saving human efforts and developing better task-specific agents as we continue to create agents for a diverse set of applications. Yeah, the coding, I hate to be like, they took my job, because I am one of those like freelance writers and proofreaders and editors that is getting forced out of the market, but seeing as my coding is so bad, I'm like, yes, please help me code. Please, please help me code. Okay, so performance. Man, we changed this next to the original generated name, but some more confusing. So again, we have structured feedback. Okay, so we sort of went over what these were, I believe, in Figure 1. So if you don't remember what that is referring to. In previous sections, we illustrated that meta-agent search can find effective agents for individual tasks. In this section, we further demonstrate the transferability and generalizability of discovered agents. To show that the invented building blocks and design patterns are generalizable, we conduct experiments on the transferability of the discovered agents. Transferability across foundation models. We first transfer discovered agents from GPT 3.5 to other foundation models on ARC to test whether agents found when performing meta-agent search with one foundation model generalized to others. We test the top 3 agents with the best test accuracy evaluated GPT 3.5 on ARC, and then transfer them to 3 popular models, Claude Haiku, GPT-4, and Claude Sonnet. We adopt the same baselines as those used in ARC and MGSM. As shown in Table 2, we observe that the searched agents consistently outperform the hand-designed agents with a substantial gap. Notably, we found that Claude Sonnet, the most powerful model from Anthropic, performs the best among all the tested models, enabling our best agent to achieve nearly 50% accuracy on ARC. Next, we transfer the discovered agent from the MGSM domain to other math domains to test whether the invented agents can generalize across different domains. Similarly, we test the top 3 agents from MGSM and transfer them to 4 popular math domains, GSM-8K, GSM-Hard, and SVAMP, and ASDIV, and 3 domains beyond maths adopted in Section 4.2. As shown in Table 3, we observe a similar superiority in the performance of meta-agent search compared to baselines. Notably, our agents improve accuracy by 26% and 13% on GSM-8K and GSM-Hard, respectively, compared to the baselines. More surprisingly, we observe that agents discovered in the math domain can be transferred to non-math domains. Huh, that's neat. While the performance of agents originally searched in the math domain does not fully match that of agents specifically designed for target domains, they still outperform in reading comprehension and multitask or match in science and state-of-the-art hand-designed agent baselines. These results illustrate that meta-agent search can discover generalizable design patterns and agenic systems. And why couldn't it? Machines and robots are very good at patterns. And here's yet another exciting Table 3 as to performance in different math domains. So those of you that are into this, I'm sure you have a nice long look at that table. Feel free to pause. Alright, related work. Researchers develop various building blocks and design patterns for different applications. Important building blocks for agenic systems include prompting techniques, chain of thought-based planning and reasoning methods, reflection, developing new skills for embodied agents and code, external memory and retrieval augmented generation, tool use, assigning foundational models in the agenic system with different roles, enabling them to collaborate, and enabling the agent to instruct itself for the next action, etc. While the community has invested substantial effort in developing all the above important techniques, this is only a partial list of the discovered building blocks and many more remain to be uncovered. Therefore, in this paper, we propose a new research area, ADIS, which aims to invent novel building blocks and design powerful agenic systems in an automated manner. So AI generating algorithms and auto-machine learning. Following the lessons learned from the history of machine learning, research in AI-generating algorithms and auto-machine learning continually strives to learn more components in AI systems to replace handcrafted ones. There are mainly 3 pillars in this field: meta-learning architectures, meta-learning the learning algorithms, and generating effective learning environments and training data. Oh my god, I thought educational pedagogy was hard. Alright, for example, neural architecture search aims to automate the design of neural network architectures like convolution, which falls under the first pillar. Now, the interesting thing is, I'm like getting into it more because I like neuroscience and spent way too much time studying neuroscience for no particular reason. Not professionally, just, reading fun, nerdy science books. Where was I? Okay, the second pillar includes works like MAML and MetaRL, which allow learning to learn for better sample efficiency, generalizability, and continuous learning of multiple tasks. Additionally, works like Poet and OmniEpic under the third pillar aim to generate learning environments in an open-ended manner. We believe the proposed automated design of agenic systems belongs to both the first and second pillar. Pillar 1 because ADIS learns the architecture of agenic systems, but also Pillar 2 because agents are proficient and in-context learning, thus ADIS can also be considered as learning to learn as demonstrated in the ARC challenge. So we have agents from math domain to non-math domains, still doing really good. Alright. Additionally, recent AIGA and AutoML works have incorporated foundation models to write code. For example, in FundSearch and EOH, foundational models write code to discover better optimization algorithms. In DiscoPop, foundational models program the loss function for preference learning and foundational model alignment training. Additionally, Eureka and Language to Reward enable foundational models to write reward functions for reinforcement learning and robotics. Finally, OmniEpic enables foundational models to create robotics learning environments by programming in code. Here we adopt a similar idea that enables foundation models to program new agents in code. Existing attempts to ADIS. There are two categories of works that can be considered attempts at ADIS in the literature, those that learn better prompts only and those that learn more components and agents than just prompts. Most works fall into the first category, learning prompts only. Works like Opero, Prompt Breeder, and Self-Discoverer adopt foundation models to automate prompt engineering for agents, primarily focusing on the phrasing of instructions in the prompt to enhance the reasoning capability of agents. Thus, the learned prompts are domain-specific and difficult to generalize. Beyond instructions, works like Evo Agent and Agent Verse optimize role definition in the prompt, as assigning personas or roles to agents has been shown to be beneficial. Although tuning prompts effectively improves performance, other important components in agenic systems remain fixed and hand-designed, vastly limiting the space of agents that can be discovered. There are far fewer attempts in the second category, which involves learning more components than just prompts in agenic systems. Most represent agents as networks or graphs in the search space. In these formulations, the foundation model with a certain prompt is considered a transformation function for text on nodes, and the information flow of the text is considered as edges. Dylan starts with a fully connected feed-forward network and uses foundational models to score the response quality of nodes in each layer to prune connections. DSPY first generates a set of possible nodes and then optimizes across the Cartesian product of those nodes while optimizing a few shot examples for those nodes. GPT Swarm represents an agenic system in a graph with a predefined set of nodes and uses a reinforcement learning algorithm to optimize the possible connections between nodes while optimizing the prompt for each node in a separate stage. Although these works allow the learning of control flow, optimizing edges in networks or graphs, many other components such as whether and which tools to learn or even how many nodes to have are still not learned, greatly limiting the space of agents that can be discovered. Besides learning prompts and control flow, Agent Optimizer learns the tools used in agents, and Agent Symbolic Learning learns prompts, tools, and control flow together. While Agent Symbolic Learning shares similar motivations to learn more components and agents, it manually designs the search space for each component separately, which may make it a harder search space for search algorithms. In addition, it mainly improves agents based on existing complex agent without showing the emergence of new design patterns or building blocks. In contrast, our work represents all possible components in the code, allowing the search to be easier by leveraging human efforts in the existing code base of agents and functional models' expertise in coding. We also demonstrate how novel and diverse building blocks and design patterns emerge from a set of basic agent designs, illustrating the potential creativity that can emerge from ADS. Alright, discussion and conclusion. So, safety. We strongly advise researchers to be aware of the safety concerns when executing untrusted model-generated code in meta-agent search and other research involving code generation. While it is highly unlikely that model-generated code will perform overtly malicious actions in our current settings and with the foundation models we use, such code may still act destructively due to limitations in model capability or alignment. Ideally, sandbox environments can be used to safely run untrusted model-generated code. Don't break our stuff. But they're going to anyway. More broadly, research on more powerful AI systems raises the question of whether we should be conducting research to advance AI capabilities at all. That topic clearly includes the proposed automated design of agenic systems as a new area in AI-GA research, which could potentially contribute to an even faster way to create artificial general intelligence than the current manual approach. The question of whether and why we should pursue artificial general intelligence and AIGA has been discussed in many papers and is beyond the scope of this paper. They're just going to kill us all. That's why we shouldn't be making the thinking robots. Specifically as regards ADIS, we believe it is net beneficial to publish this work. First, this work demonstrates that with the available API access to powerful foundation models, it is easy to program powerful ADIS algorithms and to do so without any expensive hardware like GPUs. We feel it is beneficial to let the community know that such algorithms are powerful and easy to create so that they can be informed and account for them. Moreover, by sharing this information, we hope to motivate follow-up work into safe ADIS, such as algorithms that conduct ADIS safely during both search itself, i.e. not risking running a harmful code, and that refuse to create dishonest, unhelpful, and/or harmful agents. Such an open-source research approach to create safe ADIS could be a safer, better way to create safer AI systems. One direction we find particularly promising is to simply ask the meta agent search algorithm to be safe during training and only create helpful, harmless, honest agents, potentially incorporating ideas such as constitutional AI. Oh, that's interesting. I should look up that. Yeah, that follows the Constitution would be pretty cool. I mean, we don't necessarily do that now, as people. Anyway, future work. High order ADIS. Since the meta agent using ADIS can program new agents, is also an agent, ADIS can become self-referential, where the meta agent can be improved through ADIS as well. Be an exciting direction to have a higher order meta learn to allow the learning of the meta agent and even the meta agent up until we all become gods. Okay. Seeing ADIS with more existing building blocks. Although we can theoretically allow any components in Agenic Systems to be programmed from scratch in the code space, it is not efficient in practice. No duh. Therefore, it would be interesting to explore ADIS by standing on the shoulders of existing human efforts, such as search engine tools, retrieval augmented generation, or functions from existing agent frameworks like LangChain. Additionally, it is interesting to support multimodal capabilities in foundation models or allow different foundation models to be available in Agenic Systems. This will enable the meta agent to choose from different foundation models flexibly according to the difficulty of the instruction and whether data privacy is a priority. Multi-objective ADAs. We only considered one objective, performance, to optimize in this paper, but in practice, multiple objectives are often considered, such as cost, latency, robustness of Agenic Systems. Thus, integrating multi-objective search algorithms could be promising. Novelty search algorithms. In meta agent search, the design of the search algorithm is relatively simple, focusing solely on exploring interesting new designs. A more careful design of the search algorithm may be a promising future direction. For example, one could incorporate more sophisticated ideas from quality, diversity, AI generating, and open-ended algorithms. One could also include more classic approaches to balance exploration and exploitation. More intelligent evaluation functions. In this work, we simply evaluate discovered agents on the evaluation set and use the numerical performance results. However, this approach is both expensive and misses a lot of information. A promising future direction is to enable the meta agent to analyze detailed running logs during the evaluation, which contain rich information on the failure and success modes for better debugging and improving Agenic systems. Also, many tasks involve subjective answer evaluations that do not have ground truth answers. It is also important to design novel evaluation functions and ADIS to address these tasks. Finally, in this work, we targeted only one domain during the search. It'd be interesting to explore whether ADIS algorithms can design even better generalist agents, when specifically searching for agents capable of performing well across multiple domains. More complex domains. Additionally, we only evaluate meta-agent search on a single-step QA tasks in this paper. It'll be interesting to extend the method to more complex domains, such as real-world applications involving multi-step interaction with complex environments. Understanding the emergence of complexity from human organizations. Beyond potentially saving researchers' efforts and improving upon manual design of agenic systems, the research in ADIS is also scientifically intriguing as it sheds light on the origins of complexity emerging from human organization and society. The agenic system is a machine learning system that operates primarily over natural language, a representation that is interpretable to humans and used by humans in constructing our organization and society. Thus, there is a close connection between agenic systems and human organizations as shown in works incorporating the organizational structure for human companies in agents or simulating a human town with agents. Therefore, the study in ADIS may enable us to observe how to create a simple set of conditions and have an algorithm to bootstrap itself from simplicity to produce complexity in a system akin to human society. And that, kids, is how we got to the hologram we are today! It's okay. I'm a little weird, better than life. As are all of us, right? Okay, so there is a better understanding of foundational models, so works from neural architectural search show that by observing the emerged architecture, we could gain more insights into neural networks. In this paper, we also gain insights about foundational models from the results. For example, the best agent with GPT 3.5 involves a complex feedback mechanism, but when transferred to other advanced models, the agent with a simpler feedback mechanism, the more refinement becomes a better agent. This shows that GPT 3.5 may have a worse capability in evaluating refining answers, so it needs a complex feedback mechanism for better refinement, while other advanced models benefit more from a simpler feedback mechanism. Conclusion: in this paper, we propose a new research problem, automated design of agenic systems, which aims to automatically invent novel building blocks and design powerful agenic systems. We demonstrated that a promising approach to this is to define agents in code, allowing new agents to be automatically discovered by a meta-agent, programming them in code. Following this idea, we propose meta-agent search, with the meta-agent iteratively builds on previous discoveries to program interesting new agents. The experiment showed the meta-agent search consistently outperforms state-of-the-art hand-designed agents across an extensive number of domains, and discovered agents transfer well across models and domains. Overall, our work illustrates the potential of an exciting new research direction toward full automation in developing powerful agenic systems from the bottom up. And then we have some nice acknowledgments from folks in Canada, the Vector Institute, generous donations, and all these people whose names I'm not even going to try to pronounce. So good for you. We have a lot of references, and we do have, and I'm just going to pull this down so folks can see it if you do want to go find the paper. Oh my god, so many references! So many references. Just want to get down to some of the supplementary materials. So we have prompts, we have framework code, the experiment details for the actual challenge, the experiment details for reasoning and problem solving, baselines, example agents, and then general cost of experiments. I'm just going to go down to example agents for a hot second. Okay. Yeah, critique instruction, refine instruction. Okay, so yeah, this is what they're talking about with natural language processing. So we get foundation model, thinking, answer, for roll in. This is the part I'm like sketch on. So foundation models, I assume, is something you have to build in order to feed it like training data. I need to build something, I think, is the answer to this. Deja, build something so you can have some idea of what's going on here. For in range, for in length to length, for in range, thinking, append the answer, return the answer. Okay. I'm not going to keep playing with this because my coding, as I already pointed out, is pretty weak. So it's kind of interesting on the cost, though. Single run costs approximately $500, and OpenAI API costs, while run on reasoning costs about $300. Primary expense comes from querying the GPT 3.5 Turbo model during the evaluation. Notably, the latest is one through the price, offers better performance. And again, we're back down to the incredible joy of technology disbursement, where everything starts becoming cheaper and cheaper and cheaper, and smaller and smaller and smaller. So if you hung out for all of this exciting automated design of agenic systems and want to comment on something more sophisticated, then we can use the bots to build better bots, and we're going to quickly be out-evolved. Please feel free. Thank you for sticking with me for 40 odd minutes.